Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. So today we're going to look at an aspect of the Riemann series. In our first discussion we had looked at the concept of the Riemann series for the closed intervals between A and B. And we said that this can be given in terms of subdivisions which are going to range between x0 for A, and then we're going to have this one extended to a value of xn, which is going to be equivalent to b. So these specific divisions are going to form a range of partitions, which we are going to refer to as p. And in this specific case, we had given a particular interpretation of the largest subdivision that is going to be given as the maximum. And this was going to be a range of or rather the division that is going to be given in terms of this range of values. So we're going to consider these specific differences for those partitions give the maximum as delta xk. So we said that we can be able to give this delta xk for a value of xx. This is xk minus 1 and then xk given as such. So the difference between xk and xk minus 1, which is going to form our division or an arbitrary division, perhaps, which is the maximum, then we can be able to give it as xk minus xk minus 1 given as this. So this is going to be given as the norm of P, which is the largest subdivision in this specific case for this range of closed intervals for P, A and B. So in our second illustration for the geometrical interpretation, we're going to use a function, and this basically is going to be a curve that is going to be illustrated as a curve, or rather a function which is going to be a curve and consideration with the x-axis. So I'm going to give an example of this, whereby we're going to have this one illustrated as a function, of course, which is ranging between those intervals. So I'm just going to give a different one. I just give a function which is going to be given as this. I'm going to expand this one. So I'm going to create these closed intervals between A and B given as such. So therefore, these are going to give me the values of x from x1 to xn given as such. So therefore, we're going to see that for my values, I'm going to have the first being given as x0 starting from this point, and therefore b is going to be equivalent to xn given as such. So for us to find or rather have an interpretation of this specific series, we say that we can be able to give the Riemann series in terms of the summation of from b to is equals 1 to n over the range of values for x, w, k, a change in k given as such, whereby for these specific variables, or rather the range of values for this Riemann series, we can be able to have a geometrical interpretation of what these values basically entail. So we said the concept of going to give it as such, and the p, of course, is going to be an integer that's going to range between 1 to up to this value of n that I've given as such. So therefore, if we try to consider it in terms of a graphical representation of this specific function for f of x, and therefore we can be able to visualize this value for w as a value that is going to be given. So we said that in order for us to find a and a curve, we're going to consider several partitions of this specific curve, and we're going to have a range of rectangles which we can consider to be this, whereby the division between this specific length between this one and this one, if we consider to be the width of a rectangle, is going to be given using the delta k, which is this specific point. So the delta k is going to be, of course, achieved if we have, as I've said, this is specific range of values for delta x k minus, so sorry for that. If you have a range of values for x k minus x k minus 1, this is going to give us the difference. And if this is the case, then it means that if we are going to consider the kth rectangle in this specific case, we're going to have the value of xk at this specific point, and this value before xk is xk minus 1. So the difference between the two are going to give us the delta k, the delta xk that I've given in this specific case, and that of course is going to be that second part of the Riemann series that I've given at that specific point. So this is going to be basically the change in k, and then the height of this individual rectangle is going to be a particular center point that we're going to demarcate as a w. So for the first one, it's going to be w1, w2. So for the kth rectangle, we're going to have that value indicated as wk. So therefore, it's going to be along this specific function, we're going to have it illustrated as a function of wk given as such. So if you try to look at the interpretation of the normal way in which we can be able to denote functions for the value of x and y, so therefore this is going to form our y, and therefore the delta x is going to form our x respectively. So in this particular case, then therefore we can be able to give a general representation for the definite integral over this Riemann series in terms of the integral over a to b given as the function of x dx given as such. So for our substitution for this between the closed intervals a and b, we can be able to write it as the integral of a to b of a function wk d. So this for dx is going to be the change in k, change in xk given as such. So we're going to see that one later. But of course, I'm going to also to greater emphasis that for us to find this specific sum for these rectangles, it's going to be a summation from w1, or rather from w1 to the final a bit of w n at the end of this specific value for p. So therefore, that is going to be applicable for any range of numbers or statements or partitions of this specific series. So perhaps I can just give an example whereby we're going to see that for a function that is defined on these closed intervals for a and b, and we're going to see that if the number of statements or the rectangles are going to be represented by k, we can be able to give this specific summation for that number of k for the limit of the partition of the norm of k, the norm of p for the summation over this specific range of rectangles for wk, and this is going to be the change in xk, and this is going to give us what we refer to as the limit. So basically, whenever we are trying to consider a range of values that exist in between this difference between, or rather the delta xk, which we have basically defined as w. So I've given this example for this one as w1. So for the range of values that are going to exist in between x and xk minus 1, which are delta xk, for n range of numbers, we are going to see that for every a number that we can arbitrarily give as epsilon, which is greater than 0, that is going to exist in between this particular difference for this delta xk. And there's going to exist another value that we can be able to give later. This is a sigma, that also is going to be greater than 0, such that the norm of that specific discussion, the norm of this specific partition within this specific interval can be given as the norm of p, which is going to be, of course, smaller than sigma. So basically, we're trying to limit, try to find, or rather try to give a condition for this value of the norm of p, whereby we have said that for n range of values, whereby there's going to be this specific equation that we have given for the limit of p, for the norm of p as it tends to the limit of the norm of p as it tends to k, we're going to see that the summation of f wk delta xk is going to be referred to as the limit of that particular function. whereby we have said that for this specific limit, there is going to be a value that we're going to refer to as epsilon, which is going to be greater than 0, that is going to exist, and another value of delta, which is going to exist, such that the partition over that specific function, which is of course the norm of p is going to be greater than delta, and therefore this is going to create the condition for that specific value for the limit. So we are going also to see that for any trace of these values of wk that I've indicated on the board, for this interval of xk, k1, of this range of partitions that I've given, of course, this particular value is going to exist, which we are going to refer to as the limit. Therefore, we can be able to give an expression for this specific condition for the limit. So perhaps I'm just going to do this one away, whereby we're going to see that the summation over k fwk x k is going to be given as a value that is smaller than epsilon, and that is going to apply for a range of values that are going to exist in between these specific numbers. And of course, this value for k that I've given is going to be referred to as the limit over Riemann's sum. So later we're going to see an expansion over this specific condition for limit, and perhaps some of the areas that we're going to use in trying to express this Riemann sum is going to assist us, particularly in terms of application, is going to assist us try to pinpoint what this aspect of the limit is. Now that I've introduced this value for epsilon and delta, perhaps we're going to do some of the, of course, practical examples which are going to assist us define the concept of the limit in a broader way. So that is it for now. Bye. God bless you. Catch us in our next video.